Welcome to this MathWorks presentation on design and optimization of miniaturized antennas with MATLAB. My name is Giorgia Zucchelli and I've been with MathWorks since 2009 when I started as an application engineer here in the Eindhoven office in the Netherlands. Since 2013, I am the technical marketing manager for MathWorks RF and mixed signal product areas. If you have any questions concerning this presentation or related topics such in the RF and mixed signal space, please feel free to directly contact me via email. You can see my email address here on the slides. In the next half hour, using MATLAB examples, we will describe how you can use MATLAB for antenna design. We will start by choosing the antenna geometry, then we will discuss how you can shrink the size of your antenna. We will use, for example, high permittivity dielectric materials, and we will also increase the fidelity of the antenna model by including conductor losses. We will also see how optimization techniques can be applied to improve the antenna performance. And when the finalized geometry has been determined, we will discuss how to generate Gerber files to fabricate printed antennas. Finally, we will conclude this presentation and share some additional information for you to get started. Miniaturized antennas are a requirement for wireless portable devices, such as communication, localization, or power transfer systems. There are a number of techniques that allow you to reduce the size of an antenna. This might include structural modification or using lump component loading, or make use, for example, of high permittivity materials. For example, you can reduce the size of an antenna using slots, slits, meanders, and novel geometries like fractals. However, often decreasing the size of an antenna results in a direct reduction of the bandwidth and efficiency. So as an antenna designer, we need to evaluate the trade-offs between the antenna size and its performance. In this presentation, we will introduce MATLAB for the design of miniaturized antennas and optimization. Before we go through the specific workflow details, however, let's start with a simple example. The MATLAB Antenna Toolbox helps you with the design of antennas using electromagnetic analysis techniques. If you are not an EM expert, or if you are an EM expert but have not used Antenna Toolbox, you can start from the Antenna Designer app. The Antenna Designer app provides an intuitive interface that guides you through a typical antenna design and analysis workflow. Let's start with a new design. You can select an antenna configuration from the catalog of elements, each parameterized in geometry. For example, we can choose a horn, different patch microstrip configurations, or a fractal antenna. In this case, we choose a fractal Koch antenna and design it to be resonant at 2 GHz. On the left, we see the geometric properties of the antenna. In this case, the shape is constructed with 2 fractal iterations. We set the frequency range of the analysis to be between 1 and 3 GHz and computed the antenna impedance to verify the resonance frequency. The Antenna Toolbox uses the method of moments technique to analyze the antenna. As you can see, the EM analysis is executed very rapidly, and we can verify that the antenna is resonant around 2 GHz, where the reactance is 0. Additionally, we compute the S parameters of the antenna to verify the matching bandwidth. We can zoom in the region where S11 is smaller than 10 dB, and we can estimate that the bandwidth is approximately 100 MHz. We can also plot the far-field radiation pattern at 2 GHz and see that the antenna directivity is 1.93 dBi. To this point, the antenna metallization used in the analysis has been a perfect electrical conductor, or PEC. As such, conductor losses have been neglected. We tile all figures so that we can view all of the antenna analysis plots simultaneously. Let's now evaluate what happens when we change the number of iterations for the creation of the fractal shape. We start from 1. Notice that the antenna length does not change. However, with a lower number of iterations, the geometry is simplified, while the resonant frequency and the bandwidth increase. As we increase the number of iterations to 2 and then to 3, we see that the geometry becomes more complex, the resonant frequency and bandwidth are both reduced, while the far-field pattern and peak directivity remain almost unchanged. We can increase the number of iterations up to 4, which results in a meandering structure. The analysis time for this more complicated structure is increased. However, you can still get a result in a matter of seconds. You can now intuitively understand how increasing the number of fractal iterations is a technique to miniaturize antennas, as it reduces the resonance frequency at the cost of a narrower bandwidth. For this example, we evaluate the performance of a fractal coax antenna that makes use of 3 iterations. The resonance frequency is 1.8 GHz, and the resulting antenna directivity is approximately 1.89 dBi. We can now determine the impact of a metal material with finite conductivity. There is a readily available catalog of metals that include the most common conducting materials such as copper, aluminum, gold, silver, and others to choose from. Let's see what happens when we change the electrical conductor to copper. The analysis is still very fast, thanks to the method moments. We notice that the resonance does not significantly change. However, as a result of the conductor losses, the bandwidth has increased slightly. Let's repeat the analysis in case you missed a change in the S-parameter plot. Also note that when finite conductivity is specified, the peak value of the far-field pattern is reported as gain rather than directivity. The gain value includes the finite conductivity losses. As expected, the peak gain is reduced and is now approximately 1.68 dBi at 1.8 GHz. If we zoom into the antenna impedance plot, we see that the antenna is resonant at 1.8 GHz, but is not perfectly matched to 50 ohm. This can be improved with a matching network or by adding a lumped component on the antenna surface. To demonstrate what happens when we add a lumped component on the antenna surface, we added 20 ohm resistors at the antenna feed point. The real part of the impedance is now 50 ohm as desired, and the bandwidth has also increased and exceeds 100 MHz. Let's pause here for a second and let's recap how you can use MATLAB and Antenna Toolbox for antenna design. Antenna Toolbox is your one-stop shop for antenna and array design in MATLAB. It provides a catalog of elements to rapidly get started, select and analyze different antenna configurations. It also includes the method of moments, along with other EM solvers to analyze antennas. You can also analyze the impact of installing an antenna on a large platform, such as a plane or a car. The same approach can also be used to compute the radar cross-section of a target. You can optimize the antenna performance using surrogate optimization methods based on machine learning techniques. We will see this. And you can also fabricate printed circuit board antennas by generating Gerber files. And you can also integrate your antenna into system simulations. An example of this is where you want to include the behavior of the RF transceiver so as to model and evaluate hybrid beamforming systems. And finally, you can position the antenna on a 3D terrain, determine coverage and link performance. We have seen how the Antenna Designer app can be used for rapidly get started. You define the specifications, choose the type of the antenna, and you get an initial design with the correct geometric properties. You can view the results for both near and far field analysis, and then you can iterate on the design. From the app, you can also generate MATLAB scripts for a programmatic approach towards design. The app provides access to a comprehensive catalog of antennas, each with parameterized geometry. In addition to the catalog of antennas, you can also include the impact of reflectors or backing structures with different shapes. And with each new release of the Antenna Toolbox, new antennas are added to the catalog. You can now see here in this slide some of the latest antennas, such as one based on dielectric resonators or Vivaldi architectures. If you want to design an array of antennas and compute the effects of coupling in between elements using EM analysis, you can make use of the Array Designer app. The Array Designer app is very similar to the Antenna Designer app. The major difference is that you will find the array catalog next to the antenna catalog. You can design linear, rectangular, and circular arrays. Along with a uniform array configuration, you can also analyze conformal structure, even with different antennas. And you can also analyze very large structures using the infinite array approach. In the snapshot here, you see some of the typical array analysis that can be performed with the Array Designer app. For example, to understand the coupling in between antenna elements, you can compute the far-field radiation pattern either using the method of moments or by using pattern multiplication of the isolated element. And you can also compute the pattern for each of the respective elements while embedded in the array and see how adjacent elements impact each other. With the Array Designer app, you can also compute the array impedance, the S parameters, and the correlation matrix, and these are all useful metrics to investigate coupling effects. But what can you do if the antenna that you want to design is not part of the catalog? If your antenna is not planar, you can import an STL file, a CAD format, to define its 3D geometric shape. Once you define the feed point, you can then analyze the antenna. And this approach can also be used for installation platforms. If your antenna is planar, you can use geometric shapes to define the metal layer representing the radiating element. You can specify shapes such as a rectangle, circle, ellipses, along with Boolean operations to sum, intersect, or subtract them. There is also a unique workflow that makes use of the image processing toolbox, where you can define the boundary of a shape using the photo of an antenna. Once you define the shape of the antenna, you can add a backing structure and specify the properties of the dielectric material that the antenna is mounted on. Once you specify the antenna feed point, you can then analyze your antenna. In this example, you see an antenna with a rectangular and a circular slot designed using basic shapes. Again, if your antenna is planar and it has multiple dielectric and metallization layers, or if it makes uses of vias, you can use the PCB stack object. You can either start from a planar antenna in the catalog, import it in a PCB stack object, and further manipulate it, or you can start with basic geometric shapes, as described before, or you can import Gerber files that define the properties of each layer of the printed circuit board. Once in PCB stack, you can define an arbitrary number of dielectric and metallization layers, add vias, and define feed points, one or more. Let's now go through a simple example on how you can create a PCB antenna. Instead of designing an antenna in the Antenna Designer app, I'm now going to design an antenna from the command line. Let's start with designing a circular patch antenna resonating at 2.4 GHz. The diameter of a patch is approximately 3 centimeters. Let's now analyze the antenna impedance between 2 and 3 GHz, taking steps of 50 MHz. We want to modify the antenna by inserting a circular slot in the middle of the patch. The first step consists in importing the antenna element into the PCB stack object. This operation does not change the physical or electrical properties of the element, but it allows us to modify different properties of the antenna. The first step consists in designing a circle that represents the notch in the antenna. The circle is smaller than the patch antenna with a radius of 1 centimeter. The second thing that we need to do is to perform a Boolean subtraction of the shape from the top layer of the PCB stack. We compute the resulting antenna element layout and verify that this is still resonating at 2.4 GHz. We can also view the resulting pattern and antenna directivity. We can now add a dielectric layer to the stack. For example, we can mount the antenna on Teflon. By mounting the patch on a dielectric material, we can reduce the antenna height to just 1 mm and once again view the resulting structure. We can use the same approach also to add additional dielectric and metallization layers. We can now see that with the addition of a dielectric layer, the resonant frequencies has decreased, which effectively allows us to reduce the size of the antenna. This brings us to the second part of our presentation. How do we deal with material properties, namely the metallization and dielectric substrates? As we saw in this last example, Antenna Toolbox provides a dielectric catalog with common dielectric board materials. As the catalog is editable, you can define your own board material by simply providing its relative permittivity and loss tangent. Increased permittivity of dielectric materials affect the antenna performance. Actually, it reduces the propagation velocity, and therefore it enables the possibility to reduce the size of the resonator element. With a similar approach, you can also specify the metal material, choosing from the catalog or by providing your own material specifications in terms of conductivity and thickness. You may also want to note that this can be used not only to estimate the efficiency of printed antennas, but also large antennas such as horns that are often fabricated with heavy metals such as brass or steel. This brings us to the next topic, optimizing the antenna performance. Before we dive into it, let's see an example on how it can be done with the Antenna Toolbox. From the Antenna Designer app, I start with the design of a fractal island antenna with 3 iterations and resonant at 2.4 GHz. From the initial analysis, we can see that the antenna directivity is 4.6 dBi. The impedance match along with the bandwidth of the antenna is not very good, and the area of the antenna is approximately 30 square centimeters. The goal of the optimization is to minimize the surface of the antenna while improving its gain and bandwidth performance. This is not an easy task to achieve via conventional means, as the design space is very large. We first select our objective function. In this case, we want to minimize the area of the antenna. Then we select the optimization variables that we want to sweep. For each optimization variable, we need to provide an upper and lower limit. We can optimize geometric properties as well as material specifications and lumped element values. But in this case, we just choose to optimize the shape of the antenna. For the length and width, we provide a minimum bound of 10 and max of 50 mm, which is slightly smaller than the current value. For the slot length and width, we provide a smaller range, so 1 and 5 mm respectively. We also enable the ground plane length and width optimization. We set the bounds to 50 and 100 mm respectively. The ground plane, in this way, will always be larger than the patch antenna. We apply these changes, and we now specify the optimization constraints. To improve the current gain, which is 4.6 dBi, we set a constraint for the gain to exceed 8 dBi. We add one additional constraint to improve the input match and set the S11 to be smaller than minus 10 dB. We now apply these constraints. We also change the frequency range to fewer points, so in this way the optimization will be faster. The final parameters that we need to set is the number of iterations for the optimizer. We increase the number of iterations to 300 and enable parallel computing to achieve an additional speed up. Even if my laptop only has 2 cores, this is already beneficial. Let's start the optimization. And as it takes a few minutes, while we wait for the results, let's discuss the underlying technology of the optimizer. In the meantime, we can also see the progress of the convergence. We have seen how to rapidly get started with antenna optimization for the most common use cases. The same optimization capability is also available, by the way, with the Array Designer app. From the app, you just open the optimization tab, and for the Array Designer app case, actually you will find additional objective functions and constraints that are specific for Array. Both the Antenna Designer and the Array Designer apps support the SADEA or SADEA optimization method. Other global optimization methods could also be used. The steps to set up the optimization are straightforward. You first choose the objective function. You select the optimization variables and define their upper and lower bounds. You provide constraints and then let the optimization algorithm do its job. SADEA is a surrogate optimization method that uses machine learning. Surrogate optimization methods are often used to solve problems that are computationally expensive to evaluate, such as EM analysis. Especially when many design variables are involved, even just a single iteration can be very time-consuming. The other advantage of surrogate optimization methods is that they are not based on gradients, and therefore the probability of finding a local minimum is reduced. Additionally, these methods also work on problems that are non-smooth. The main idea behind the surrogate optimization methods is that they use a surrogate model for the objective function, and the surrogate model is faster to evaluate. This surrogate model also gets regularly updated during the optimization, and as a result, fewer EM analyses are required for the optimization of the antenna performance. If your optimization problem requires a configuration more complex than the one allowed by the app, or if you are an expert in setting up optimization, you can customize the objective function, and you can use any of the methods provided by Optimization or Global Optimization Toolbox. And you will find several examples showing this custom workflow. We can see now that the antenna optimization is completed. Let's go back to our demo. We see that the progression towards convergence and the results achieved with 300 iterations. We can accept the results and verify the antenna performance. As you can see, the antenna is still resonant at 2.4 GHz, and the S11 behavior has significantly improved. The directivity of the antenna has also significantly improved. The gain now exceeds 8 dBi. We can change the metal to copper and determine the antenna efficiency. As you can see from the results, the antenna's electrical performance has significantly improved on all fronts, and the antenna size is now smaller than 8 square centimeters. This brings us to the final part of this presentation and the antenna design workflow, that is to say, antenna fabrication. We have already seen how the PCB stack object can be used for the design of multi-layer antennas. We will now see how it can be used to generate Gerber files for PCB fabrication. The steps are straightforward once you have designed a planar antenna with PCB stack. First, you select the online PCB service. This is very convenient for inspecting the generated files before sending them to the manufacturer. Second, you choose the connector and how it gets connected to the board, whether it gets soldered on top of the board or on the side of the PCB. Third, you can generate Gerber files. You'll get all of them in the working directory, and then you can share them directly with the manufacturer. And by the way, this is the same process that we used in MathWorks to verify many of the designs done with Antenna Toolbox. I would like to conclude this presentation by summarizing what we have seen today. We saw how MATLAB can be used for antenna design, and we examined the drivers behind miniaturization, such as using fractals, slots, and mounting antennas on dielectric materials. We were able to estimate the impact of conductor losses by using metals with finite conductivity and thickness. We were also able to evaluate how the antenna performance is impacted by the use of dielectric substrates. We also use the surrogate optimization methods to improve the antenna performance and at the same time reduce its size. And as a final step, we discussed how Antenna Toolbox facilitated the antenna fabrication workflow via the Gerber file generation. With that, I thank you very much for your attention, and I encourage you to try Antenna Toolbox and MATLAB and other MathWorks products in your next wireless system design. I would also like to suggest to recommend you to explore the numerous examples that come along with Antenna Toolbox. These examples cover many of the topics that we discussed today, but you will also find lots of interesting things that for sure you will like to see. If you have any questions, please don't hesitate to reach out. Thank you again.